Hello, and welcome to this edition of the Gen Z tutorial video series. This is one of a series of videos that introduce Gen Z. What is it? What problems does it solve? What are some of its high-level attributes and capabilities that make it a powerful solution for next-generation infrastructure? This video series is made in 3 parts. Gen Z, a new approach, provides an introduction to the challenges being faced by today's infrastructure and why Gen Z offers an opportunity to drive new levels of innovation. The Gen Z tenets provides a list of architectural tenets that drove the design, protocol definition, and specification of Gen Z. And finally, there are a series of videos for a number of Gen Z use cases, which are examples of how to apply Gen Z technology into various real-world infrastructure components and solutions. Today, we present Gen Z, a new approach. So let's get started. This video describes some of the key trends in the IT industry and the challenges faced by today's infrastructure to keep up with these trends. We will take a brief look at how Gen Z can be applied to next-generation infrastructure to break existing limitations and drive new levels of innovation, efficiency, performance, and reliability to deliver the workloads being demanded by IT customers. First, let's take a look at a couple of key trends in the IT industry. Everyone has probably seen this chart in one form or another, as it is a hot topic in all the trade rags and industry publications, analyst reviews, etc. The data explosion problem is self-evident even to the average person on the street with the advent of social media and all of the personal content they are generating. In addition, the Internet of Things, or IoT, is an emerging field where there'll be monitoring and control of everything from appliances, security systems, manufacturing lines, energy generation and distribution systems, transportation systems, and so on and so on. Well, it's obvious that the amount of data being generated and stored and analyzed in the next generation infrastructure is going to be phenomenal. This massive increase in the amount of data generated is one thing, but what we are finding is that an estimated 37% of all data generated will have some sort of significant business value. And that leads us to the chart on the right, which depicts the need to analyze the data even faster than ever before to provide real business value and insight from the data being collected so that it can be applied to operations and the business of carrying on a successful business. The data must be analyzed in a timely manner as its value decreases over time. So as the old saying goes, time is money. Well, these two trends multiply the challenges for today's infrastructure to deliver the business results required in a timely and cost-effective manner. For an example of the stresses these trends have on today's infrastructure, one only needs to look at the evolution of the traditional two-socket server over the last 10 years or so. We will begin by examining a two-socket server from circa 2008. In this time frame, typical CPUs had 2 DDR memory channels per socket and a high-performance link to a North Bridge, which provided the PCI Express or PCIe links for connectivity to embedded NICs and storage devices, and the PCI Express slots for I/O expansion, for example, NICs, GPUs, storage adapters, etc. The adapters in the PCI Express slots would translate PCI transactions to protocols such as Ethernet, Fiber Channel, SAS and SATA storage protocols, etc. In this time frame, a small handful of cores were available per CPU. Bus and interconnect protocols that were present in this time frame included DDR Gen 2 and 3 memory channels, PCI Express Gen 2, SAS and SATA Gen 2, etc., as shown here in the bottom of the slide. But as the popularity of server virtualization and increased workloads per server swept the industry, more cores were supported per CPU, and a greater number of faster DDR memory channels and PCI Express I/O links were required. This diagram of our dual-socket server circa 2013 illustrates the growth to 4 DDR channels per CPU. Furthermore, the North Bridge was integrated into the CPUs, and the number and width of PCI Express links supported per CPU socket increased. Each of these changes caused the size, pin count, complexity, and cost of the CPUs and the motherboards to increase significantly. The increase in memory and I/O bandwidth was necessary to feed the bandwidth requirements of the additional CPU cores to minimize the time they were stalled waiting for data. Bus and interconnects such as DDR4, SAS and SATA Gen 3, and PCI Gen 3 were introduced in this time frame, as seen here on the bottom of the slide. One of the interesting trends that occurred with the introduction of DDR Gen 4 is the drop in the number of DIMMs per DDR channel that was typically found on servers, from 3 DIMMs per channel to 2. This was because the increased speeds and electrical challenges was necessary to lower the DIMMs per channel, thus driving the requirement for more DDR channels per CPU socket to maintain and increase memory capacity. Now, in circa 2016, the CPUs expanded to 6 DDR memory channels per CPU socket and added additional PCI links, lanes, widths, and slot count. CPUs also integrated SATA links to support low-end storage requirements. DDR Gen 4 was now prevalent, and additional interconnects, such as GPU-specific NVLink technology, emerged. Another technology that emerged in this time frame was NVMe, which allows solid-state disks, or SSDs, to be accessed directly over PCI without conversion to SAS or SATA protocols. The number of CPU cores was increasing at an ever faster rate than the memory and the I/O bandwidth of these devices. Again, the CPUs had significant growth in size, pin counts, complexity, and cost. This also increased the complexity and cost of the motherboards for these servers. Finally, in circa 2017 to 2019, we will see CPUs that support 8 DDR channels per CPU socket and 64 or more PCI Express lanes per CPU. In this case, most of the PCI expansion is to support the requirements for greater numbers of NVMe SSD drives directly connected to the CPUs. In this time frame, PCI Gen 4 will emerge. All of this memory and I/O bandwidth is necessary to support the continuing rise in the CPU core counts. At this point, we see that processors are well over 4,000 pins, and their size, complexity, and cost continues to rise. Finally, on the horizon, we see another generation of interconnects and bus technologies coming up, including DDR Gen 5, SAS and SATA Gen 4, and others, like GPU and coherent interconnects like C6 and OpenCAPI. We have an ever-increasing number of protocols and interconnect technologies being used to connect components in our 2-socket server. As these boards add these faster and more complex technologies, the systems are becoming much more complex and costly to manufacture. To highlight the trends we saw in the last slide, let's look at a couple of charts that help visualize these challenges processor architectures face. The graph on the left is a normalized measurement of several properties of a typical server class CPU, where the vertical axis depicts how much of an increase in each property has occurred from 2012 levels. From this graph, we can see that over the last several years and out to 2019, there is a significant rise in the number of DDR channels and PCI lanes on these CPUs, between 1.5 to 2 times the number of channels or lanes available back in 2012. Factoring in data rate increases, the total bandwidth of each of these would be somewhat higher, but not by much. One will notice that we pay a price in the number of CPU pins required to maintain these increases in memory and I/O bandwidth. Over 4,000 pins will be common in the near future. This graph also indicates the CPU core counts are growing much more rapidly than the memory and I/O capabilities of these same CPUs. The differences in these rates of increase can be seen in the graph to the right. This graph uses the calculated memory and PCI I/O bandwidth of the CPUs over the course of time and divided this by the number of cores available in that generation of CPUs, yielding the memory bandwidth per core and I/O bandwidth per core available with each generation of CPU. The trend is undeniable. Even though the CPUs are becoming more powerful, we literally cannot keep the CPU cores fed with the data as well as we used to, leading to more CPU stalls and lower CPU utilization per core. We see that there was a small respite in this trend when 6 DDR channels were introduced circa 2016-17, but the rapid increase in CPU cores will swamp any benefits of moving to 8 DDR channels in the future. These trends are not sustainable. There needs to be a better way of providing the bandwidth to satisfy the ever-growing appetite for memory and I/O bandwidth on these massive multi-core processors in order to provide efficient processing of the explosion of data and the small windows of time for analysis we discussed earlier. Beyond the internal interconnects within a server, the manner in which the servers are connected together to share data and work together to perform the required workloads is also facing challenges looking forward to the near future. Today, a number of different fabric and networking technologies are employed to connect servers and data storage systems together. We have Ethernet as a general purpose network, Fiber Channel SAS and SATA for block storage connectivity, InfiniBand and OmniPath for high-performance computing and low-latency messaging, and even PCI Express is used in limited circumstances as a fabric technology. But each of these were created for specific purposes, and none of them behaving as a true memory semantic fabric, to speak the native language of a CPU, which is load-store, read-write, reading and writing bytes and or cache lines at a time instead of blocks or messages. The ability to be a memory semantic fabric is critical when we move from block file and object-based storage to memory-based storage facilitated by byte addressable persistent storage class memory, or SCM, which we'll discuss shortly. If we take these network and fabric protocols and add them to our list of the internal server interconnect protocols here on the bottom right, what you'll see is that we have the proverbial Tower of Protocol Babel. Every time data is moved and converted from one protocol to another, this adds complexity, power, cost, and management overhead. There has got to be a better way to evolve this infrastructure to become something more streamlined and optimized for the coming data-centric or memory-centric computing paradigm occurring in the near future. There's another trend that is also putting pressure on the architecture of today's infrastructure. Here's an illustration of the different classes of memory and storage device technologies in use today. On the left are the internal processor registers or memory blocks with sub-nanosecond access latencies. Then there are the integrated or external SRAM devices, typically used for caches, that operate in the 5 nanosecond or less latency range, but still have very low load-to-use latency. Next is DRAM, which is typically external to the processors with higher latency in the 100 nanosecond range, but still provide excellent load-to-use latency on average when placed behind cache memory. All of these memory types are byte addressable and volatile. That is, any data stored there will be lost with unexpected power cycles, system errors, system shutdown, etc. On the right-hand side of the chart, there are the persistent memory technologies that are accessed as blocks of data, and they typically have much higher capacity and higher latencies than volatile memory types. Flash memory, i.e. memory used in solid-state disks or SSDs, is fast by storage standards at 100,000 nanosecond access latencies, but this is very slow compared to our volatile memory types. Traditional hard disk drives and tape drives round out the block devices category. but the access speeds here are glacial compared to our volatile memory devices. Another problem with block access devices is that studies have shown that the vast amount of data brought into a server via block accesses is discarded without being processed. For example, in sparse data searches, where you're bringing in blocks of data looking only for a few pieces of it, and then throwing away the rest without even looking at it or processing it. This is challenging for maintaining memory bandwidth for data analytics workloads. Storage class memory is an emerging technology that looks to bridge the gap between these two classes of memory. SCM memory types include phase change, spin torque transfer, resistive memory, 3D crosspoint, etc. It has both persistent and byte addressable properties, and their latencies are somewhere between DRAM and flash memory latencies, but closer to flash initially. As storage class memory technology matures, the access latencies will continue to get closer and closer to DRAM latencies, and will eventually provide a near memory alternative to DRAM technology. At this point, storage class memory provides the best of both worlds and offers a vision to memory storage convergence. This evolution will drive a new class of computing that is often referred to as data-centric or memory-centric computing. The figure on the bottom here illustrates a possible progression of memory storage convergence internal to a typical server over the course of time. Today, servers are composed of external DRAM memory and a combination of solid-state disk drives or SSDs and hard disk drives. In the not-too-distant future, as the adoption of storage class memory begins, it will start to displace some of the SSD and disk drive capacity in a server. A little further into the future, both on-package memory, or OPM, and storage class memory will start to displace some of the DRAM capacity in a server. On-package memory is highly optimized memory that is faster and wider than external DRAMs, and are co-packaged as stacks of memory die on the CPUs. They are already used in GPUs today, but OPM can't provide the capacity of external DRAM. So storage class memory can serve as the high-capacity off-die memory for CPUs. This will be possible because storage class memory latencies and bandwidth will continue to improve over time. At the same time, storage class memory will continue to displace SSD and disks for data storage purposes internal to a server. Finally, some analysts envision that over the course of time, processors will have only integrated on-package memory and external storage class memory to provide memory expansion and primary storage, while a small amount of SSDs are used for bulk storage. Hard drives, traditional disk drives, will be relegated to external cold storage systems. So storage class memory and memory storage convergence will impact our server architecture, and the main question is, where can we place storage class memory in our server architecture to maximize its effectiveness? Let's go back to our server architecture figure and examine this question. First, we can place storage class memory on the PCI Express bus. Typically, this is in a storage class memory PCIe card plugged into a PCI Express slot as shown in the figure to the right. A storage class memory PCIe card offers good capacity and decent performance for early storage class memory technology that has higher latencies. It's an industry standard form factor, which is also positive. However, this option limits the locations where the storage class memory card can be placed due to strict PCI bus routing rules, and this limit will become much more challenging as PCI Gen 4 and Gen 5 are introduced. In addition, the PCI bus is not built for reliability, where multiple links or paths can be deployed to ensure memory connectivity. Finally, the PCI cards are stranded resources on the local processor, as the storage class memory cannot be accessed in a byte addressable load store manner from any other server. Sharing the memory requires more complex protocols like remote direct memory access, or RDMA. Another possibility is to place the storage class memory on the processor's DDR memory channel in one of the DIMM slots, as shown in the illustration to the right. Persistent memory DIMMs are commonly called NVDIMMs, short for non-volatile DIMMs. One class of NVDIMM uses DRAM memory that is backed up to flash memory if power is lost or the system is shut down. These DIMMs are called NVDIMM-N. Typically have lower capacity than standard DIMMs because of the persistency circuitry, but they are very fast and operate well on the DDR channel. Another type of NVDIMM are NVDIMM-P DIMMs that utilize storage class memory natively. These DIMMs have logic that allow the storage class memory to operate on the DDR memory channels. NVDIMM-P have good capacity, although not as high as PCI cards. The challenges with NVDIMM-P is that the CPUs have to be made to slow the DDR channels down to allow the slower storage class memory to operate correctly. This also eliminates the ability to share the DDR channel between NVDIMM-P DIMMs and standard DRAM DIMMs. This means that we're sacrificing precious DRAM memory channels for the capacity and persistence of storage class memory. So storage class memory is not a great fit for DDR memory channels, as placing them there is a somewhat unnatural act. Storage class memory on DDR channels also suffer from the same reliability problems that PCI does, but even more limited placement restrictions of DDR DIMM slots. Finally, storage class memory on the DDR channels are also stranded and can be only accessed by the local processor and cannot be shared by other servers in a byte-addressable load store manner. So what's the solution to all of these challenges? We need a new universal interconnect and fabric technology that is memory semantic. It needs to facilitate the language of processors, byte-addressable, load store operations that drives the new data-centric, memory-centric computing model that will power next-generation workloads. Here are some of the key attributes that this new technology needs to embody. It must be high performance, high bandwidth, low latency, and scale from motherboard to chassis level to rack scale to row scale. Bandwidth to feed the ever-increasing core counts in future processors of the future, but more efficiently, with less power and lower costs than the trajectory of technology evolution we're on today. It must be reliable and secure. If we are connecting persistent memory to a fabric to be shared by many processors, it had better have rock-solid reliability and secure enough to prevent inadvertent or malicious accesses to business-critical data. You can think of these features in a similar way that we make reliable and secure high-end storage systems today, but for memory. It needs to be flexible. To be able to implement this technology in as many places as possible throughout the infrastructure. It needs to be able to allow SoCs and CPUs, memory, and I/O devices of multiple generations and types to be connected seamlessly together. It needs to support direct attachment of SoCs to memory and I/O, as well as enable a fabric where multiple SoCs can provision and share memory, accelerators, and I/O devices dynamically through the entire lifecycle of the workloads being hosted on this infrastructure. It needs to support gateways to traditional network and storage infrastructure to provide access to legacy storage, fabrics, and internet-based resources. It must facilitate compatibility with existing unmodified operating systems and applications, such that these can take advantage of the new infrastructure built with this technology, yet benefit from the features and capabilities it has to offer. Then, over the course of time, the operating systems, applications, middleware, and APIs can be adapted to take the maximum advantage of the capabilities of this next-generation technology. It needs to enable frictionless adoption by IT customers and infrastructure operations teams based on where they are in their journey to data-centric, memory-centric computing. It needs to be economic and provide greater workload efficiency to achieve dramatic increases in data processing, get business-critical answers much faster, all without an equivalent dramatic increase in costs. And finally, But most importantly, this technology must be open. We want the IT infrastructure and component suppliers and the IT community to all be participants in the definition and implementation of this technology so it is ubiquitous and operates in many different market segments across a broad range of workloads. So, what is this technology? It's Gen Z, the universal system interconnect and fabric technology that is built from the ground up to be open, high performance, reliable, secure, flexible, compatible, and economic. Gen Z can power the next generation of data centric and memory centric computing to deliver the workloads required well into the future. To give you a sample of what Gen Z technology can do for you, let's take a look at how Gen Z can be used for memory interconnect between a CPU, for example, and memory components of various types and generations. In the figure on the top left, we see a DRAM DIMM connected to a CPU, processor, SoC, or other host component. Let's just call it an SoC for now, system on a chip. The SoC has both an integrated memory controller for managing memory operations to external memory and the media controller, logic block, which actually understands the DDR bus interface and protocol, which is native to synchronous double data rate DDR DRAM memory. Since the media controller is integrated into the SoC, this means that the SoC and external memory modules are forced into lockstep as far as technology evolution are concerned. In addition, this limits the types of memory that can be supported by the SoC at any point in time. These limitations are illustrated in an animated figure in the upper right-hand side. The SoC and memory must progress over the course of time in technological lockstep. This limits innovation and system flexibility, making it difficult to quickly adapt to changing workloads and market requirements. In addition, the memory types that can be supported by the SoC are baked in when its design is completed. Thus, it cannot support different types of media that are introduced long after the SoC's design cycle is completed. Again, this severely limits innovation. Now let's take a look at how Gen Z can help alleviate these limitations. Watch the animation carefully on the left as we transform the static memory interconnect into a dynamic universal memory interconnect. This animation depicts the fundamental architecture change where media controller is migrated from being integrated into the SoC to being integrated into the memory module itself. Gen Z logic blocks are added to both the SoC and the memory controller to allow a memory agnostic asynchronous protocol to facilitate high-performance memory accesses from the SoC to the memory module. This change allows us to do two important things. First, we unlock the lockstep innovation between SoCs and memory, and the SoCs and memory can evolve completely independently of each other. Second, we can now support a wide range of memory technologies, which is especially important for storage class memories, where there are many variants with different attributes that may be required for different workloads. Thus, an SoC can support memory generations and types not comprehended in its original design. This capability enables a new level of innovation for memory and host component development. Furthermore, this paradigm shift applies to I/O and scalable fabric-based communications in addition to simple memory interconnects. This is just one sample of the type of transformations Gen Z enables for next-generation infrastructure technology. We would like to invite viewers to take the next step in your journey to discover Gen Z by watching the next episode of this series titled The Gen Z Tenets, where you will learn about the key attributes and requirements used to guide the design of the Gen Z protocol and architecture. After watching this video, viewers will better understand the true power and capability of Gen Z technology and how it can dramatically improve the performance, efficiency, reliability, manageability, and total cost of ownership of next-generation infrastructure. We hope you've enjoyed this episode of the Gen Z video tutorial series, and thank you for joining us.